So right, so I was talking about concurrency. Um, the way that I'm going to organize this week is today I'm going to talk about the basics of concurrency, which for some of you probably already know this, and maybe for others you have never had been exposed to a formal course that taught you these kinds of things. So it's just to put everybody on the same page. And then on Thursday, I am going to focus on how to get concurrency under control with specific styles of concurrency. And some of them made it to programming languages. Others you just use certain libraries that give you that kind of style of keeping threads under control. So without further ado, let me go back here to my first set of slides on concurrency. And this is really just the basics. And literally, concurrent programming is, in one way or another, the bottom line is that when more than one thing is happening at the same time in your software, right? In software that you write, then you have more than one thing at a time. So examples, network server handling hundreds of clients, right? So concurrent requests that are being processed at the same time, or data processing that's spread across multiple CPUs, or an application receiving input from several peripherals like the mouse and the keyboard and other things like that. So there's concurrency can happen at many levels, okay? And I will talk a little bit about that, but then I will talk about the user level concurrency. But there's more levels where concurrent things happen. But in sort of general terms, if you have just the idea of concurrency is not necessarily the same as parallelism, okay? And there's two slightly different things. They're related, but two different things. So concurrency is two things at virtually the same time, not necessarily at physical same time, okay? So it depends on how many processing units you have. So if you have just one processing unit, then and if you want to run two things at virtually the same time, then you have to share this processing unit, right? So somehow you have to have some sort of a switch, a scheduler of some sort that runs thing one for a little while, then they switch to running thing two for another little while, etc. So this is one way of supporting concurrency, even if you just have one processing unit. Okay, that's the concept of a scheduler is really important. If you have more than one CPU, then basically, and if you just have, for example, if you have two CPUs and if you have two concurrent things, then this is parallelism. Okay, this is true concurrency, meaning that there's really two things happening at physical same time, right? You don't need to share. If you have more than two things and you only have two CPUs, then you do the scheduler, the switching between the tasks that you need to run, just like in the previous slide. This scheduler, all right, this is an important part of any operating system or virtual machine that supports concurrency, all right? Again, as I said, concurrency happens at many levels, from the low levels of the operating system all the way to languages that support threads. Okay, and I'm going to talk about this. But whenever you have concurrency and you have to share the processing unit, you have to have a scheduler. That's the definition in software. That's the word that is used to describe that piece of software that manages and switches between the things that you want to run concurrently. Now, another thing that is important to know about your programs that affects the way that you think about the concurrency model that is applicable to your concrete situation is, what is it that these tasks are doing? Because concurrency is not all the same. Okay, so tasks may be doing roughly two things. They may be processing, okay, doing math basically using the CPU, or they may be just waiting for things to happen, right? Waiting for data to arrive, waiting for a packet to arrive on the network, waiting for the data from the disk to actually be brought into main memory. So there's a lot of waiting in programs, even though it's, in our time scale, it's super fast, but in the scale of computers, actually waiting for I/O is very slow, super slow. So typically, our programs have a mixture of processing and I/O. And this is important to know, and it's important to know the kind of profile of your program that you have at hand, because that influences, the kind of threading on how many threads does it make sense, given what your program is doing and given the hardware that you have at hand, right? So, for example, if you have a CPU bound task, that's basically some programs that are very CPU intensive. And by this, I think it's things like, for example, doing math or doing image processing, or even the neural network stuff that's or Bitcoin mining and stuff like that. So these are CPU bound tasks. They are constantly using the CPU. All right, and why? And then there are other tasks that are very I/O intensive. These are, for example, network servers, okay? Web server or any other kind of network service, highly I/O bound. That's the technical term, I/O bound. Because most of the time, it's just waiting for data to come. And then it just runs something, and then it's waiting for data to come again. And why is this important? Because it's important to know the kind of profile that you have, whether it's I/O bound or CPU bound or a mixture of the two, and what kind of mixture it is. Because, for example, if you're dealing with a program that is mostly CPU bound, there's only so much that you can do in terms of speeding things up by having many threads, right? Because you can things only make sense if you have, for example, an 8 CPU machine. You have 8 CPUs available, and your program is highly CPU intensive. Then there's no point of having more than 8 threads, right? In fact, if you have a lot more than 8 threads, what will happen is that your program is going to slow down, because there's the thread switching, right? The thread switching, the scheduler, is a heavy duty thing. So you want to avoid thread switching as much as possible. So if your program is highly CPU intensive and you're limited, you should know what kind of hardware you're dealing with, how many CPUs you have, and then the number of threads cannot be very high. Otherwise, your performance goes down. On the other hand, if you have a server, if you're dealing with a server that's mostly waiting for data, even if you have a lot of clients at the same time, right? If you have a lot of clients at the same time, but mostly the server is waiting for the data to arrive, then it makes sense to actually have a lot of threads, right? You can have more threads than the CPU, then, because they are already ready to run, and basically most of them are going to be waiting for I/O anyway. So it's not going to be overwhelming the scheduler. So it's important to know, how many threads does it make sense to have in your program? It depends very much on what your program is doing, and how many CPUs you have, and how many in what your program is doing. So it's important to know the balance between CPU usage and I/O waiting. Okay, so another thing that it's important to understand is the kind of data sharing that is going on between these concurrent things. So first of all, when you have concurrent things, these concurrent things are related somehow. Okay, so they are related somehow, even if it's at the operating system level, or especially if it's inside your own program at user level. But if you have concurrency at user level, then clearly they're related, and very likely they need to know about data that is common between these two threads. So there's the memory model of concurrency is something that is really important to really understand what is, what's the best way of sharing data between concurrent things. So one way is to have shared memory, what's called a shared memory. And this is, for example, when you have inside a process in an operating system, your process, it has just one address space for memory, and everything, if you run concurrent things inside your process, then that process is going, those things are going to share the data, that they are all part of the same process, right? So there's a immediately, anything can access can have the capability of accessing the same data. Another model is separate processes on, for example, the same machine. So separate processes on the same machine. Now you don't share the memory. Each process has its own memory. You can still share data by using some sort of inter-process communication. And this could, every operating system has its own version of inter-process communication, or you can use, local sockets is another very widely used way of sharing data, on local host. So this is a clear, separation between the things, even though they are related somehow. They share data, but the way that they share data is very constrained and is explicit, right? It's explicit. So if thing 2 wants to share something with thing 1, it actually needs to work for that to happen, as opposed to the first model, in which it's implicit. Any concurrent thing can access the data. And then finally, the most separated version is when you actually have processes, different processes, not just in the same machine, but in separate machines. Okay, this is distributed computing, right? So distributed computing is when you have actually physical different hardware, and in order to send a message from one process to another, you need to go through the network. Yeah, okay, and this is really network programming, so sockets or something like that. So this is all part of concurrency. Okay, this is all, they basically things that are concurrent and somehow related, because they need to share data one way or another, and how related they are, it depends on what they are doing and what what the goal of the application is. But so this is roughly the shared memory space. This is the model of threads that I'm going to talk about for the rest of the lecture. This one is typically called parallel computing. So this is when you have a same physical machine that has a lot of CPUs, but they all have they're all the same on the same motherboard. So this is called parallel processing. And then you have distributed computing, which is different machines that need to use a network in order to talk with each other. So for the remainder of the lecture, I'm going to talk about the first thing, so the shared memory. I'm not going to talk about network or distributed computing, and I'm not going to talk about parallel processing either. I'm going to talk about shared memory, the first one. So when you have several things happen at the same time inside the process. Now, if you remember the simplified machine model, this is all happening, in modern computers, this is all happening in the same process. So you have registers, you have code, you have the stack and the heap data. It's all inside the same process, right? And so what are threads? So if you look I should probably put a separator here. If you put on the left side, this part of the picture, the common model of a program is that you have, this is, up here are the things that were on the previous slide. So the code, the heap, files, the stack, the registers is all here. And then you have a thread of execution, one single thread of execution that uses all of that, all the code and the stack and stuff like that, the heap. Right, so this is a single-threaded program. So what are threads? A multi-threaded program is basically certain things are still shared, and those are the ones here. So the code is shared, the heap is shared, the files are shared, but certain things now are separated. And what is separated? Mostly it's the stack, okay? The register too, but the stack is the important thing. Basically, you can almost say that a thread is basically a stack. It's a separate stack, okay? And with some sort of, an agency of execution that is scheduled by the scheduler, right? So basically, this is a picture of a multi-threaded program. Is when you have, where you basically create multiple stacks, and each thread now has its own stack that is separated from the others. However, the code and the heap are still shared. And the heap in particular is important because this is where the objects are, right? The objects that are created dynamically, right? The memory, okay? And this is important, and I'll tell you a little bit more about the dangers of that. So what are the benefits of threads? Responsiveness. So you can have, especially if you're doing things like GUIs, things that happen. I'm sorry. Good job. That was my daughter being annoying. So things that happen concurrently in the natural world. So, for example, events from the peripherals, for example, right? So the mouse and the keyboard and things like that, or the networks and stuff. So if you are able to immediately process those without waiting for other things that may be happening, then you get the better responsiveness of your program. Another thing is for resource sharing. So sometimes you are dealing with a piece of data, and that piece of data is important for many different tasks, right? And instead of replicating that data everywhere, you have some sort of data in one place, and then the different things that need access to that data are just sharing that data instead of having multiple replicas of the data. So that's another benefit. And also performance in multi-core machines is another benefit, although I have it in parentheses because it really depends. This is where I'm warning you, because it depends on what your application is doing, the kind of profile, the ratio of I/O versus CPU. So there's a fine balance in here for how much performance you can gain out of multi-threaded programs. It also depends on the language. Okay, I will talk a little bit about that. So for example, Python is very famous for not being very good in terms of multi-threading. So Python has multi-threading, can have many threads in Python, but there's something in Python that's called the global interpreter lock, GIL, that completely defies the idea of actual parallelism. So even if your machine has many CPUs, there's only so much that you can do, because as I said in here, the threads share the code. And in Python, every access to the code is kind of locked by a global lock. So if every thread that is going to go through the same code has to wait for each other. So Python has a really weird, made a really weird decision for, there's lots of stuff out there on the internet that you can read up, but why Python does this. But so Python is not very good for, in terms of threads, especially for CPU bound threads. You don't really gain much from having multi-threaded programs in Python. You can still gain if your program is IO bound. So IO bound, it's still a good thing, but not for CPU bound things. So the pitfalls are threads are race conditions, and I'll talk more about that in a second. Because now several things are happening at the same time, and accessing the data at the same time, you have to look at your program in a completely different way with different classes, basically, with the classes that two threads may be accessing the same data at the same time. It's much harder to understand, to kind of keep track of the sequence of execution, because the sequence of execution may actually not be deterministic. There's a lot of things now that you don't control, because there's a scheduler underneath, and the scheduler is also not deterministic, because it depends on what else is going on in the entire machine, right? Because it's the lower level of the operating system scheduler. And so it's suddenly you are in a world that things are not deterministic. And what that means is that your program can run for a very long time perfectly fine, and then something, after, for no reason, it crashes and it has the bug, and then you cannot reproduce it anymore. It's very hard to reproduce. So they're called Heisenbugs. They're very hard to reproduce. Another pitfall of threads is that it's very easy to end up with a colossal mess in your code of synchronization primitives and locks and stuff like that. It's really, really, it can be really bad. And another thing that you should be aware is that creating threads is a heavy-duty process. So if performance is an issue, then the way to do it is to use what's called thread pools, which are arrays of threads that are created in the beginning, and then as you need them, you allocate things to them. Okay, so this is called a thread pool. But creating threads dynamically is a heavy-duty process. All right, so and another thing that I want to clarify where we are in the map is that there's actually two types of threads. There's the user level threads, and then there's what's called kernel threads. Okay, those are sort of the hardware threads, and I'm not talking about those. So sometimes when you spec a computer, a machine, you have, you know, whatever number of CPUs plus whatever threads. Those are kernel threads. Those are things at the hardware level. That's not what I'm talking about. I'm talking about the user level thread libraries. Okay, things like the POSIX, the P threads in the C world, Java threads, .NET threads, Python threads, all of that stuff up at the user level, and that is usually exposed in the programming language, either directly in the programming language or through some library of some sort. Okay, so I'm going to give you some API examples, thread API examples, and these are typical of most modern programming languages, okay? And they come in two flavors. So the way that you create threads, if you have never done that before, or even if you have done in one language, you should know that there are basically two ways of creating threads. There's a functional API, and then there's an object-oriented API. And you know, you can recognize them, and some languages provide both, like Python, for example, provide both APIs. Others provide only one. So C++ and C provide the functional API. Java and C# have a object-oriented API. Python has both. So there's different things, but they all kind of converge more or less to the same kinds of things. That's why I'm going to explain this in Java, but it applies to the object-oriented APIs that some languages provide. So here's one example of creating threads. So one way is that you have so the languages that provide this API, the object-oriented API, typically have some sort of an interface called runnable or whatever. I think in Java it's called runnable. In C#, I forget. It's probably called runnable too. But so this is an interface. It's not a class. It's an interface. Just saying that, and this interface usually has some mandatory methods. In this case, it's a run method. You know, the runnable has a run method that comes from the runnable interface, and this is the method that gets invoked eventually as sort of the main thing that gets called to after the thread has been created. So how to create a thread? So if you have a runnable of some sort, you can create a thread in Java and C# and Python by instantiating an object of a class that is given by the standard libraries that usually called thread. Okay, so in all of them there's a thread class. Okay, in these APIs, and so you create a thread, and the way that you need to do this, at this point, there's still actually the parallel execution still does not exist. So basically, that's why I find it useful to kind of visualize the thread as a stack. Okay, actually, it would be better if they would just call this stack anyway. So at this point, you don't have the parallel execution yet. You just created a thread, meaning that you created a separate stack. Okay, that's basically what it is. And then to start the thread, you actually need to start the thread. So there's a method called start in these APIs, and this is when you actually kick it. Okay, and in this case, notice that when you created the thread, the first argument is a runnable object. Okay, happens to be this, could be any other object that is a runnable, that has a runnable interface. So what that means is that when you start the thread, it goes down to the virtual machine, and then the virtual machine calls back the runnable method of this object that you gave it. Okay, which in this case it's this runnable this run method. Okay, so in this case, then it's going to loop 5 times, and it's going to sleep a little bit, and it's going to print something on the screen. Okay, so it's just going to loop 5 times, and it's going to exit, and that's all it does. So this is a way of creating a threads in the object-oriented style APIs of all the modern languages that I know. And so here's a main method that exercises that code. So in here you just say you create one of those threaded objects, and this one creates and starts the thread as in the constructor. It already does that, and then the main method is a separate thread. So every main method is sort of the main thread, right? If you don't create other threads, there's always one thread, which is the one that you start the execution with, right? So what happens here is that you create a new thread, a separate thread, and then you continue, right? So and in this case, you're continuing, you also iterating 5 times, printing something on the screen and sleeping for some amount of time. All right. So this is one way of creating threads. Another way that these APIs allow you to create threads is by actually extending, by declaring a class that extends the thread class already. Okay. So by doing this, then your class that you are defining is a thread, has the capability of being a thread. So in this case, you would just say, so you don't need to create a separate thread object, because by constructing this object, you are constructing the thread, and then you just have to call start, and then there's the same thing over here. Start calls the run method. Okay, and then in here it's the same, looks the same. So those are the 2 ways of creating threads in object-oriented style APIs, which is you can either declare a runnable class, and then you have to create a separate thread object by giving that runnable as the target, or you declare your own class that extends the thread class. Okay, and then you already have a thread, and you create instances of that object. All right, and then there's the whole other way of providing threads, which is functional style. Okay, and so this is true in C, C++, Perl, Racket, and basically what those APIs give you, they give you a function called thread or whatever, and what it expects is a function, right? It expects that you give it a function that is going to run concurrently, right? So in this case, you're creating a thread, and this is the function to run on that thread, okay? And same thing for C++, you have something like that. So you declare a function task1 over here, and then you declare a thread, the one that takes task1 as the argument, okay? So those are functional APIs, and Python provides both. All right, so you can create threads in Python by using the thread class, or you can create them by using something like this. So common, independent of how you start them, or what language you use, there you will find these operations on most threading libraries out there. So you can create threads, you can start them, you can sleep them, you can sleep your own thread, you can suspend, resume, yield, stop. You'll find most of these in most thread APIs. Now, what I want to talk about, I explained to you how to create threads, but creating threads is trivial and it's just the beginning, because the whole ugly side of the story comes with controlling what they are doing, and in particular controlling access to the data. So let me just point out to you that the danger of having a multi-threaded program lies in the fact that the threads share the heap and the files. They share. So basically, whenever you create an object, you're allocating memory, right? And so all of those objects now, if you pass them around between threads, you have different threads that have references to the same objects, and they can act on the same objects at the same time. And bad things can happen when you do that. So let me show you the bad things that can happen. Shared data problems. Suppose that you have some threaded object over here. I haven't fixed this yet. Okay, this is the constructor. Damn it, should fix this. I keep forgetting to update the PDF. I already fixed this in the font and I keep forgetting in the source file, and I keep forgetting to update the PDF. This is the constructor, and it takes a counter as an argument. Okay, so it takes the counter object as an argument, this constructor. Okay, and so what it does here is it holds on to the reference of that counter object. So we're going to create threads that take a counter object as a reference in the constructor and hold on to that reference. And then what they do when they run is that they update that counter. So they say increment or decrement. So in this case, they're going to iterate 500 times, and every, if it's even, it increments, and if it's odd, it decrements, and then it sleeps for some amount of milliseconds. So, and they're all going to do that. So basically, so here's the counter object. It is very simple, just has an integer, it has an increment method and a decrement method. And then you have the main method that creates this counter object, which is one object on the heap, right? This is the object that's going to be on the heap. And then it creates these 5 threads, and it gives them all the same reference to the shared object on the heap, right? So we now have 5 threads that are going to be sharing the counter object, the single counter object. And then they all execute that loop that they were doing, and then the main thread is waiting for all of those other threads to finish. So basically the picture here, you have 5 threaded objects and all of them share this counter object. Okay, this is what the situation that we have here. So what can go wrong? Well, lots of things can go wrong. So here's the counter object. So suppose, here's one possible thing that can go wrong. So suppose that T1 enters the increment method. And now here's the thing. Before I even explain this, this is how, when you have threads, you have to start looking at your code with different classes, different granularity, because you cannot, and I'll tell you why. Because if you look at this line of code, C equals C+1, and I wrote it like this on purpose. I could have written it like C++ or something like that, but I wrote it like that on purpose. You might be tempted to think that this is a one thing operation, that this is just one thing, and actually it's not one thing. There's many things going on in here. In this single line of code, there's many things going on in here. In particular, there's 3 things going on in here. The first thing that's going on is that C is accessed. So the value of C is accessed. It's read. Okay, so you go to the memory and you see what's the value of variable C. Okay, that's the first thing. The second thing is that value is incremented by 1. Right? That value is incremented by 1. That's a separate thing. And finally, the third thing is that the result of that increment is written back to variable C. Okay, the assignment. So there's 3 separate things going on, not just a unitary and indivisible thing. There's 3 separate things. And what you need to understand is that when we're talking about a scheduler and multi-threaded programs, the scheduler has the power to interrupt these things at any point. Okay? So if the scheduler decides that this thread has run enough, it interrupts it, and it doesn't care if this thread has just read C without adding and assigning. It's just read C, and then when it comes back to this thread, it will continue, by adding and then assigning. But in the meantime, it was interrupted. So that's the thing that you have to keep in mind. You have to start looking at your code in completely different classes. That your code can be interrupted at any point, and lines of code are not units of locking. Okay, on the contrary, they can be interrupted in many different ways. So having said that, let's see one thing that can go wrong. So you have one thread T1 that enters the increment method. It reads the value of C. Suppose that C had the number 3, for example, at that point. Now it's interrupted. Okay, so the scheduler decides that this thread 1 has been running for enough time, and it interrupts it, and it runs thread 2. Okay, so now thread 2 enters the method. It reads the value of C, and it's still 3, right? And now it continues, so it adds 1 to C. It gets the value 4 and assigns C to the new value. So now C has the value 4, right? And then T2 returns, and now the scheduler decides to interrupt and give the CPU again to T1. So T1 is resumed, and remember, T1 had just read the C. The C value at that point in time was 3. So when it resumes, it still has the value 3. Okay, and so now it adds 1 to the old value of C. So it adds 1, it gets 4, and assigns C to that value is 4. So basically, we lost 1 increment, right? We had 2 increment operations, but we lost 1 of them because the thread was interrupted in the middle. Okay, does everybody understand what is going on here? Any questions about this? This is what's called a race condition. Here's another one. It doesn't need to be the same method. It could be different methods for the same, as long as they use the same variables, you can get into race conditions. So here's an example. T1 enters increment. T2 enters decrement, right? So T1 reads the value of C, that's 3. T2 reads the value of C, that's 3 still. T1 adds 1 to its value. T2 subtracts 1 from its value. So now T1 has 4 and T2 has 2. And now one of them assigns it, right? And the last one that assigns the value wins. Okay, and one of the assignments was lost. So essentially one of the operations was lost in here. Right? This is also a race condition, even though it's not on the exact same code, but it works on the same variable, shared variable. So this is the source of a lot of bugs in concurrent programs, a lot of them, all right? Not all of them, but a lot of them. Basically, race conditions are corruption of shared data due to thread scheduling that we don't control because it's being controlled by the scheduler. It's very hard to deal with. It's non-deterministic. It's hard to reproduce. You can run it once and run fine, and then you can run it again and things break. And the program may be okay for a long time until it hits a race condition that is hard to reproduce. So this is the source of a lot of people banging their heads on their keyboards because they cannot find where the race condition is. It's just see that the program is not working as expected. So how do you deal with this? You deal with this with a whole set of constructs that give you concurrency control. These are a set of primitives for controlling the execution of concurring threads over the same code. All right, so basically locks of some sort. So in Java, for example, there's different ways of doing this. So one thing that you can do is to use the synchronized keyword in Java. And what this is going to do is a sort of like a guard, okay, at the entire object level. And now if you have synchronized methods, what this means is that only one thread at a time can enter the synchronized methods on the same object, okay? So basically now if you had two threads coming at the increment method, if you had them coming at the same time, it's guaranteed that only one will be here, even if it's interrupted by whatever, the second one cannot get in until the first thread has exited this code, okay? So basically you serialize the access to this code over here. And moreover, in Java and in C# too, when you have this synchronized keyword, it's actually at the object level. So if you have two threads, one coming at the increment method and one coming at the decrement method, because they are both synchronized, the second one can only get in when the first one is out. Okay, so it's guaranteed there's only one thread at a time in the set of methods that are marked as synchronized. That's what the synchronized method means. And in fact, the way that you have to interpret synchronized is sort of like this a little bit. I'll explain. So another way of doing locking in Java, a lower level API, is with the keyword lock, which takes an object. So you can just create any object and you say lock on that object, as long as it's the same lock. And now you're guaranteed to have serialized access to this code that is being locked by the same object. And a yet other level, lower level of synchronization APIs are the acquire and release of lock. So you can have a lock. Some of these languages have some sort of a lock class, and you acquire and release them. So you say, create a lock, and then you acquire it, and then you release it, and you acquire it. And now this is a little bit as we go down the level of these APIs, it starts being a little harder to get it right, because so synchronize is just a declarative thing. Okay, synchronize, that's it. This one, it's a little bit more imperative in that you have this lock statement in the code, but it's still okay because the block that is supposed to be synchronized is lexical. So there's a lexical scope, right, with the curly brackets that say from here to here, it's synchronized, and you don't need to remember to release the lock or anything, right? So in this case, this is totally programmatic. It's a very programmatic interface, and it means that the acquisition and release of the locks is under your control, which can be both a good thing, but it can also be a bad thing, because if you acquire a lock and then if you forget to release it, no other thread will be ever able to enter the code that is being guarded by that lock. So if it's the same thing with the discard with closing certain resources, like when you open a file, right? If you open a file with these old lower level APIs that you actually have to close it at the end, and if you forget to close it, then you can run out of files. So that's the same thing that is going on here. These are more powerful APIs, lower level, but they're also more dangerous because you can make more mistakes. I just heard some weird sound that looked like somebody was messaging me. I know where it came from. All right, so locks seem easy, but they're actually very hard to manage, and this is the topic of another set of bugs. So the first set of bugs come from race conditions, which happen when you don't have enough locks. And the second set of bugs come from the locks themselves, which happens when you have too many locks, or that the logic of the locking is actually incorrect. So it's a sweet spot where the program is correct. And if you have less locking or more locking than sweet spot, then you get into all sorts of trouble. So lock management is acquired locks must always be released, including when exceptions occur. And a lock that's not released will prevent any other thread from entering that block forever. So overlocking leads to deadlocks, or may lead to deadlocks. And this is an example, somewhat artificial example of how you can get into a deadlock. Suppose that you have some same increment, and increment is an artificial example, just to explain to you the mechanics of a deadlock. Now I'm creating two different objects that I'm going to use as locks. And in the increment, and in order to run the actual code, I want to acquire both locks. Okay, so, but I am acquiring them in different orders. So in increment, I'm first acquiring lock 1, and then I'm acquiring lock 2. And in decrement, I'm acquiring lock 2, and then I'm acquiring lock 1. All right. So what happens here is that you can get into a deadlock because you can have a thread that starts running increment and acquires lock 1, and then it's interrupted by the scheduler, right? And at that point, you have another thread that goes into decrement, and it acquires lock 2, which is free, right? And then it tries to acquire lock 1, but it can't because it's locked by the first thread. Okay, and then the first thread. I continue to hear these things about messages. It's so weird. Anyway, the first thread tries to run, and it tries to acquire lock 2, but it can't because it has been acquired by the second thread. So now you have a deadlock. They're both deadlocked. They cannot. None of them can proceed. And this might, this is an artificial example, but you may. I've seen code like this for things like, a typical example, still somewhat academic, might be, in a transfer money between bank accounts, for example, that you would need to acquire locks for both bank accounts, right? And so you would have two different locks, and now there's maybe other things that require the acquisition of two different locks. And if you are not careful of always having the same sequence of lock acquisition, you might end up with a deadlock. So that's a slightly less artificial example. So here's my summary about threads. They are nice, definitely very useful, but synchronization primitives are very hard to get right. You can get in both. It's like a sweet spot, right? If you don't hit that sweet spot, you can either get into race conditions or you can get into deadlocks, and they're both bad. There are many corner cases. The bugs are super hard to reproduce. Again, you can get better performance, but you can also get worse performance because if you're allocating more threads than what is justified for the kind of thing that your program is doing, then what you're doing is you're basically overworking the scheduler. And the scheduler is a heavy-duty thing. Okay, so if you have a lot of threads and you're constantly switching between the threads, then you spend a lot of time in the context switching, and that can lead to bad performance. Locking itself, by the way, is also a heavy-duty penalty. So the synchronized keyword and the lock, that is also a lot of extra CPU cycles. So locking is a heavy-duty thing too. So there are many reasons to avoid threads, or at least use them under strict constraints. And this leads to the next lecture on Thursday. So what we're going to do on Thursday is I'm going to go through a few well-known concurrency models, ways of using threads that we need to understand what are the constraints. Like, we need to have the threads under control. And there are different ways of controlling the threads in a more of a higher level kind of a thread model of the application, depending on what kinds of applications you have at hand. So that's what I'm going to talk about on Thursday. For the assignments this week, this is about concurrent programming. And so the first one is 29. Which is the actor model. So you can start already with doing 29, even though 29 is one of the styles that I'm going to talk about on Thursday, but it's a relatively basic concurrency style that for some of you may be familiar. And basically, this builds on one of the exercises that you guys already did back in the object-oriented programming week, which was the letterbox style, chapter 12. So if you go back to your exercise of chapter 12, it should be relatively easy to do chapter 29. Okay, so basically chapter 12 is a single threaded version of chapter 29. So I will talk a little bit more about actors. And then chapter 30 and 32 are two of the other styles, which are the data spaces, and then MapReduce. I'll talk about MapReduce on Thursday too. Okay, so for this week's exercises, you have to pick a language that supports multi-threading. One language that's out of the question is JavaScript. So JavaScript has just single-threaded language, so you cannot do this in JavaScript. But C++, even Go, I think it has multi-threading.
Technically, even Python is not multi-threaded.
Python is multi-threaded. It's just that it doesn't take the most out of threads. But Python is multi-threaded, and its threads are useful. So now that I talked about, let me go back. I already said this in the beginning of the lecture about.
So I'm sorry, I just joined the class, so I missed the earlier part.
Yeah. So
I had a meeting before this. So,
right.
yeah.
So Python, Python threads, as I said, are weird because they are threads, and you can definitely use them, and they are very useful, especially for servers. Okay, for things that are I/O bound, they are very useful. For things that are CPU bound, however, they are not very useful because every time that you access the code, so you have many threads, and Python has threads exactly like this picture. But so the code is shared, right? And which is true in Java and Python and C#, all the multi-threaded languages, the code is shared. But the thing that Python does that the other languages don't do is that every time that the thread is actually accessing the code to run, there's a global lock on the code. That basically, if you're running a conditional, for example, only one thread can be running that particular conditional. Okay, so basically, it kind of defeats it's not true parallel. You cannot have true parallelism with threads in Python because there's a global interpreter that kind of serializes all the accesses to the code. But you have threads just like the other languages. It just doesn't take the most of it because of the global lock on the code.